Hello and welcome to Unit 5. This is our first lecture of Unit 5. This is on minerals. So this unit we're going to be talking about rocks and minerals and rocks. And this is fun stuff because we're covering a lot of ground here. We're going to learn about what makes a mineral, what makes a rock, and let's jump right into it. All right, so by definition, a mineral is a usually inorganic solid that has a characteristic chemical composition, an orderly internal structure, and a characteristic set of physical properties. Okay, so we kind of break those down into these four characteristics here. Okay, so these are sort of like must-haves for something to be considered a mineral. All right, so first of all, it has to be inorganic. That means it can't be once a living thing. Okay, it can't be made by a living thing, right? Like a product, like a dried amber or something like that, or it can't be a shell from, let's say a crustacean or a mollusk that's been hardened, like a sedimentary rock we're going to talk about soon. And it has to occur naturally. Okay, so no man-made substances can be considered minerals, and it has to have this crystalline solid. All right, so what is that? So if you look at things, solids under a microscope, some solids have what we call amorphous shape. Their particles are kind of randomly around an area, not really much of a pattern to them. But to be considered a mineral, you have to have sort of this sort of more orderly, rigid structure, right? The atoms are actually kind of arranged a little bit more in a pattern. Now this makes the substances stronger. You're going to find this in what we call crystalline solids. All right, so that's another requirement for minerals, and it has to have a consistent chemical composition. So it has to mostly be one type of thing. Okay, so we can't really have mixtures or composites or kind of mashups. It's just got to be one type of substance, just about. Okay, so those are the four things we kind of give it a test. Okay, so we're going to be doing this quite a bit. We're going to kind of test and see if something is a mineral or not. Okay, we're going to think back to that definition. All right, so here's what we're going to do. We're going to give these five substances here the test to see if it's a mineral. Okay, so we'll start with coal. Okay, so coal is, you kind of burn it for fuel, and we use it in factories still, believe it or not. Is it inorganic? That's our first question. So here are the questions here we're going to ask, right? So these four questions here, 2, 3, 4. So is it organic? No. So coal is not inorganic. It's made from the decomposed, pressurized remains of living things. Okay, so the bones and skeleton and skin and plants and stems and all that stuff from living things get crushed down, under layers and layers of rock, right? So the dead things are down here. Then the rock layers lay on top of those, and they pressurize them into coal over a long period of time, which then we take and burn in our smokestacks and whatnot. Okay, so coal is not a living thing. Sorry, coal is from a living thing, so it's not inorganic. So it fails the first test, so it's not a mineral. Brass, is it inorganic? Yes, it is. It's not made from a living thing. It's not made from, it's not a product of a living thing, so far so good. But does it occur naturally? No, it doesn't, right? So brass is made up of a combination of zinc and copper, all right? So people, human beings, make brass. So it does not occur naturally. You can't dig up and find brass, in the Earth's crust. So we'd say it is not occurring naturally. It fails the test. Okay, so even though it does pass one of the requirements of a mineral, if any of these are negative or turn up as a no, it's not a mineral. Or how about obsidian? Obsidian is that beautiful glassy, black-looking rock. What is that? Let's see. So is it inorganic? Okay, yes. It's not made from a living thing. Okay, does it occur naturally? Yep, you can go kind of near a volcano and find some of it. But is it a crystalline solid? No, right? So if you looked at obsidian under a microscope, you'd see this sort of almost glass-like in order to its particles. It's not arranged in an order. It is kind of all over the place. So we say that it is not a crystalline solid, so it is not a mineral. All right, so we are 0 for 3 so far. These are all not minerals. How about basalt? We've measured some basalt, right? It's a nice dark rock, you know, kind of looks like it's definitely inorganic. Yep, it's a rock, right? It's from cooled magma, so it's not an organic substance. Does it occur naturally? Sure, you can find it in the crust of most oceans. Is it a crystalline solid? It actually is. So if you look at it, it's very orderly, very strong. It's got that strong crystalline type structure, but does it have a consistent chemical composition? No. So basalt found in different parts of the world is made up of different ratios of different minerals and other elements, okay? So it's not always the same. So basalt isn't the same if you dug it up in Mexico than you would dig it up in Japan, right? So whatever crust it comes from might be slightly different in its mineral content. So we can't say basalt is a mineral, not a mineral. How about fluorite? All right. Is it inorganic? Okay, sure is. Not made from a living thing. Does it occur naturally? Sure, yep, it sure does. Is it a crystalline solid? You can actually even see it right there. It looks like crystal-like. It's got that consistent structure in its atomic structure. And does it have a consistent chemical composition? It does, okay? So no matter where you find fluorite in any part of the world, wherever it's mined, it is the same chemical makeup, okay? So it is, let's switch to a green. It is a mineral. Hooray. Huzzah. The kinds of minerals, all right? So there's 20 of the most common minerals. Those are called rock-forming minerals because they form the rocks that make up the Earth's crust. So if you need to kind of backtrack a little bit, minerals make up rocks. So minerals are sort of the ingredients that make up rocks, okay? So there's 20 that we're going to focus on, and 10 of those are so common that they make up 90% of the Earth's crust. So these are quartz, orthoclase, plagioclase, muscovite, biotite, calcite, dolomite, halite, gypsum, and ferromagnesian. All right, so these minerals are the 10 big ones, the big 10, in terms of making up 90% of most of the ground that we walk on. Okay, all minerals can be classified into two groups: so silicate minerals and non-silicate minerals, based on their chemical composition. So if you're a guessing man, you can probably guess that the silicate minerals have silicon, and the non-silicate minerals do not. All right, so we'll start with the non-silicate minerals. All right, so, excuse me, we'll start with the silicate minerals, sorry. The silicate minerals are a mineral that contains a combination of silicon, or Si in the periodic table, and oxygen, and also may have some metals like potassium, which is symbolized with K, or sodium, which is Na, or calcium, which is Ca. Okay, so you're going to have a combination of a metal combined with this non-metal here, silicon and oxygen. All right. Common silicon minerals include quartz. Right, I'll show you an example of that in class. It's a beautiful clear crystal. Feldspars and ferromagnesian. Silicate minerals make up 96% of the Earth's continental crust. Okay, so we're talking about what we would call, maybe land, right, on the continents, and certainly not limited to the land we walk on, is made from silicate minerals. So quartz and feldspar make up 50% of the crust. So a huge chunk of the crust is made is made from those two. Okay. Okay, so non-silicate minerals. Those are minerals that do not contain compounds of silicon and oxygen, quite obviously. And when we talk about non-silicate minerals, we're talking about 4% of the Earth's crust. Okay, so we said before that the other 96% comes from the silicate minerals. So this is a small fraction of the rest of the crust. Non-silicate minerals are organized into 6 major groups, which we're going to use another acronym to help you remember. And these are based on their chemical composition, so the elements that basically comprise these. All right, so the 6 major groups of non-silicate minerals are carbonates, halides, native elements, oxides, sulfates, and sulfides. Okay, so we're going to remember that. We're going to reorder that to make the word chosin. So again, chosin is CHOSSEN, standing for carbonates, halides, oxides, sulfates, sulfides, elements from nature. So these are native elements or elements from nature. All right, so we're going to talk about what these are in a minute. So Just sort of practical applications of studying minerals. A mineralogist is someone who examines, analyzes, and classifies minerals, in case you're looking for a career. Each mineral has specific properties that are the result of its chemical composition and crystalline structure. Many of these properties can be identified by simply looking at a sample of the mineral through simple tests. So we're going to do a lab where we're going to give you guys like a container of a bunch of minerals, and you're going to have to sort through and give them some of these actual tests we're going to look at right now. Okay, so you won't know what the minerals are, but with these tests you can identify them. Okay, so one thing you can do is to look at the mineral's color. All right, well, color is a property that's easy observed. It's actually quite unreliable. The color can get affected by the inclusion of impurities or by the weathering process. So we talk about pyrite a lot. So I'll show you guys a sample of pyrite in class. Pyrite looks a lot like gold. That's why it's called fool's gold. All right, so it's got that gold coloration, that similar luster. We're going to talk about luster in a minute, to gold. Okay, and there's really only one way to figure out exactly which one's the pyrite and which one's the gold, and we're going to go over that in just a minute. So if you just look at their colors, they look almost the same. So color is not very reliable, but it is the first test you can give to figure out what mineral is what. The other is streak. So streak is the color of a mineral in powdered form. Okay, so we have these little things called streak plates. You take a mineral and you rub it against the streak plate, and it leaves a little, like a trail of powder. So that color of that powder is what we call streak. Streak's more reliable than color for identifying minerals. And again, we use streak. Streak is determined by rubbing some of the mineral against an unglazed ceramic tile called a streak plate. You guys will all have streak plates for the lab. All right, so the streak plate just gives you kind of a surface, a white surface, to look at that color of the powder that forms when you rub it against it. So really dense, harder minerals are going to leave no streak, so it's possible to have no streak. And then some that break down more easily are going to have leave behind more powder or a colored streak. Luster is another way to think about minerals, another way to identify minerals. So luster is the way that the mineral reflects light. Think about luster similarly as like the shine of the rock. Okay, so we call shiny objects that have a metallic luster. All right. So a mineral that's said to have a metallic luster as a mineral is similar to polished metal. All other minerals have a non-metallic luster. Okay, so we would call these maybe dull. They sort of have that non-shiny characteristic. So there's several types of non-metallic lusters, including glassy, waxy, pearly, brilliant, and earthy. So I guess earthy and waxy and pearly are more dull, but glassy kind of shines the way glass does. So quartz kind of has a glassy luster. Pearly, think about how that pearl sort of is almost a creamy white color, but still shiny. And waxy, if you guys think about kind of what wax paper looks like, or like a candy wrapper, it has that kind of opaque, which is sort of like almost a murky color to it. That would be waxy. And then brilliant is just extremely shiny. All right, so cleavage is another term. So focus on geology here, gentlemen, not the other definition of cleavage. Cleavage is the tendency of a mineral to split along specific planes of weakness to form smooth, flat surfaces. So there's a few examples of cleavage down here. So the muscovite is shown here, follows this sort of pattern here, which makes these sort of roundish oval type ridges. So it has a flat plane. Feldspar has this almost right angle kind of type of cleavage, so it tends to break off in these right angles. Halite tends to make these interesting geometric shapes here, and calcite makes these really interesting, almost parallelogram type shapes here. So if they break along one of these kind of set pattern lines, we say they have a certain cleavage. All right. If a rock has like no real pattern, or is round or really smooth, it is said to not to have cleavage. Okay. So again, here's some more sketches and three-dimensional examples here of the same rocks we just talked about. Some are at 90 degrees, some are not, and some are just flat like the muscovite. Okay, fracture is another way to identify a mineral. So fracture is the manner in which minerals breaks along on either a curved or irregular surface. So an uneven or irregular fracture have a rough surface. So here you have an example right there of an uneven or irregular fracture. You guys can see there's no real pattern here. They're kind of curved like there. You guys can see that there. But over here, a splinter, a fibrous fracture looks like pieces of broken wood. So that's actually a mineral you're looking at right there. And similar over there, you guys can see there's sort of a splintery type break there. So a curved surface, which actually is the far one over there, is called a conchoidal fracture. So the conchoidal fracture breaks in this sort of curved pattern. Okay, so curved is conchoidal. The splintery one obviously looks like splinters. And over here we have the rough or uneven or irregular fracture. So how that mineral breaks tells us fracture. It's a little bit different than cleavage. Cleavage is where there's a pattern of breakage. Fracture is how it breaks without a pattern, and there's 3 different types. Okay, so the last one is hardness. All right, so hardness is the measure of the measure of the ability of a mineral to resist scratching. So hardness does not mean resistance to cleavage or fracture. Okay, it just means does it break at all. And the hardness of the mineral is compared using the Mohs scale. All right, the Mohs scale, hardness scale, is the standard scale which all hardness of minerals is rated. So every mineral can be placed on this scale from 1 to 10, and we can rate its hardness with that. Okay, so this is like the Mohs scale. I'll show you a better picture of that in a second. The strength of the bonds between the atoms make up the mineral's internal structure and determines the hardness of our mineral. So going back to that, remember minerals have to have that crystalline structure. So if it's a more perfectly symmetrical, perfect pattern in a linear of a crystalline structure, it's going to be stronger. Okay, one that's the bonds are not so strong, where those bonds kind of are weak and break up. We're going to talk about that in a future unit, ionic and covalent bonds. But when those bonds break easily, we say it's not hard, right? So talc, for example, which baby powder was once made from, is a really, really easy mineral to break apart. Whereas diamond, which is the 10 on the Mohs scale, is the hardest one to break apart. It's the hardest mineral. Okay, so again, here is that Mohs scale. I told you it's a little bit easier one to read. So talc is like kind of like a powdery. It's easily, you can take your fingernail and scratch it. It would be a 1. So it's softer. It's lower on the hard scale. And if it's diamond, which is the hardest, we kind of use diamond as the it can scratch anything. That's why you see burglars in movies taking a diamond and scratching glass or cutting glass with it. That's because diamond is extremely hard. Now it's fictionalized a little bit. Like you can't easily cut through a pane of glass and make a perfect circle like the burglars do, but it can scratch glass easy and scratch almost anything easily. Density is the last way to identify a mineral. All right, so as you know, we've talked about density this year already. You guys know the formula. There it is right there, mass over volume. So it's commonly expressed in grams per cubic centimeter for solid. All right, so G over C3. Okay, so the density of a mineral depends on the kinds of atoms in the mineral and how closely the atoms are packed. So again, we talked about this before. It's kind of like that. What does the atomic structure look like? What does the atom of the mineral look like if you could look at it closely? If they're really packed in like this, all right, that's a really dense substance. All right, so if you took another sample of another mineral and it's packed in a little more loosely, that we'd say that's less dense. Okay. And density is great because just about every mineral has a unique density. They're not all the same, so it's a great identifier. Okay, so that's why density is useful, because it's unique to most substances. You can calculate it pretty easily by finding out the mass, finding the volume, and think about back to pyrite and gold, right? So if you look at those two and you can't tell the difference or didn't know that gold is more dense, you could get a chart, find the density of gold, find the mass of each, find the volume of each, and then you'd find out that gold is far more dense than pyrite. If you held them in your hand, it's much heavier, but let's say you didn't even have that, you just had some numbers. You could compare the densities of each and determine what is the gold and what is the pyrite. All right, so there's a couple special properties of minerals we'll kind of add on here. There's some unique sort of categories of minerals. So some minerals are magnetic. They're attracted to magnets, so that these minerals can be magnetic themselves. So in general, non-silicate minerals that contain iron are more likely to be magnetic. So magnetite is the most kind of famous example of that. And magnetism is, something you guys understand, so I'm not going to spend too much time on that. Another special property is radioactivity. So radioactivity results as unstable nuclei decay over time into stable nuclei by releasing particles and energy. All right, so they slowly become safer, but they initially have this unstable nucleus, right? And the unstable nucleus gives off energy and makes it radioactive. We use Geiger counters to determine the released particles, the rate of the released particles, and thus to identify minerals that are radioactive. That's that little device you see in movies that kind of ticks when you get near a radioactive substance. We used to have one here in McQuaid, but I think it's no longer operational. But regardless, radioactivity in minerals is pretty rare. There's only a few elements on the periodic table that even are radioactive, so we don't find it too much in the Earth's crust. Fluorescence and phosphorescence are two other special properties. So those are the ability to glow under ultraviolet light. That's fluorescence. So when you turn on one of those blue lights or black lights, that's and anything that glows is called fluorescence. Fluorescence minerals absorb the UV light and then produce visible light of various colors. So it's really beautiful. Remind me in class to show you that. We have some samples of that. The property of some minerals to grow after the UV light is turned off is called phosphorescence. So while the light is on, we would call that fluorescence, and then it glows, but then when the light goes off and it's still glowing, you have phosphorescence. So this is a little bit more rare, but pretty cool. Okay, and then the last one is this idea of double refraction. So it's a property of some minerals, and especially some forms of calcite, to produce a double image of any object through the mineral, called a double refraction. So it kind of bends light a certain way as that light passes through and creates that double image. So that's another special property, and you are done now with the lecture for lecture 2 here, or lecture 1 rather, in Unit 5. Hope you have a great night and get ready for your quiz.